I think we will go ahead and get started. It's a small group, but we are recording, and so this will go on to the NNCI YouTube channel as well. I want to welcome you all to, my name is David Gottfried. I'm the director of the NNCI Coordinating Office. I want to welcome you to another meeting of the NNCI webinar series this month in the computation area. Before I hand it off to my colleague Azad Naimi to introduce today's speaker, just a reminder that you can find links to all of our events on the NNCI events page. And if you've missed past NNCI webinars and want to view them, you can find those links on the events page, but you can also find them directly on the NNCI YouTube channel. And a reminder that there will be time for questions at the end. Just type those into the Q&A box and we will have those answered. And with that, I will pass it off to Azad.
Thank you very much, David. It's my pleasure today to introduce our speaker, Professor Steve Goodnick. Professor Goodnick is the David and Darling Ferry Professor of Electrical Engineering at Arizona State University. He served as chair and professor of electrical engineering from 1996 to 2005, and as associate vice president for research from 2006 to 2008. And currently he serves as deputy director of ASU Lightworks, as well as the DOE Ultra Energy Frontier Research Center. He's also a Hans Fischer Senior Fellow with the Institute for Advanced Studies at the Technical University of Munich. He has served as the president of the IEEE Nanotechnology Council and the president of IEEE Eta Kappa Nu Electrical and Computer Engineering Honor Society Board of Governors. He has made many contributions, including contributions to analysis of surface roughness at the silicon dioxide interface, Monte Carlo simulation of ultra-fast carrier relaxation in quantum confined systems, global modeling of high frequency and energy conversion devices, full band simulation of semiconductor devices, transport in nanostructures and fabrication, and also characterization of nanoscale semiconductor devices. He has published over 450 journal articles, books, book chapters, and conference proceedings, and he is a fellow of IEEE and Association for Advancement, the American Association for Advancement of Science, for his contributions to carrier transfer fundamentals and semiconductor devices. So we are honored to have him, and please, Professor Goodnick, go ahead.
Thank you very much, Azad, for that nice introduction. Very kind of you. So the work I'm going to talk about, Azad mentioned that I'm deputy director of our Energy Frontier Research Center and this Energy Frontier Research Center is on ultra wide bandgap devices, and so our role in that is to lead the theoretical effort in modeling and simulation of transport in such materials. And this is work that was done with collaborators at ASU, including the student and postdoc, Jonah and Reza, and Tathagata Arunamasinghe is a faculty in physics who is involved in ab initio calculations, and Marcus Arnidi has been a collaborator for a long time and helped develop the Cellular Monte Carlo method that I'll talk about today. Just some background on the motivation for what I call ultra materials. These are ultra wide bandgap materials. And a prototypical material is, for example, diamond, which I'll talk about later today. And diamond has a bandgap of 5.5 eV. And so this is in comparison to previous wide bandgap materials, such as gallium nitride, silicon carbide, which have bandgaps of about 3.2. This is almost double. And so there's a new set of very wide bandgap materials, which is shown on the right, comparatively, that have superior breakdown properties because of their bandgap. And so you should see going from gallium nitride with a bandgap of 3.4 eV, that in the same material system, in terms of alloys between gallium nitride and aluminum nitride, ultimately goes to aluminum nitride with a bandgap of 6.2. Cubic boron nitride has a band gap of 6.4. Diamond in the carbon in the diamond form has a band gap of 5.5. Gallium oxide is a new material that's showing a lot of promise, particularly for N-type devices, which are band gap of 4.8. So these are all these materials with band gaps greater than 4.5 are what we sort of call ultra wide band gap materials. Although exactly where that that band gap cutoff is a little bit ambiguous. In any case, the importance is that for power electronic applications, what's called the figure of merit, and this comes from Belaga from a long time ago, but there's other figures of merit as well. But primarily, a figure of merit for power electronic devices is that this superior performance is achieved by maximizing the figure of merit, and that depends on the breakdown voltage squared over R-on. R-on being the on resistance. This could be for a diode, it's the forward on resistance, or this could be for a power transistor, the on resistance when it's fully turned on, like the resistance associated with the drift region in a power device. And the breakdown voltage is the factor that depends most on the band gap, as you can imagine, and goes something like some power of the band gap, and therefore squaring that in terms of the figure of merit means that there's a very strong dependence on the band gap, which is why the figures of merit for these ultra wide band gap materials are orders of magnitude higher than, for example, silicon, and definitely an order of magnitude higher at least than the materials that are commercially used today, such as silicon carbide and gallium nitride. Hence the interest. So these are some of the materials that we're working on in our center, and that's cubic diamond, cubic boron nitride, and wurtzite materials of both aluminum nitride and boron nitride. And these are some of the properties of these. I won't go into detail. I'm going to focus mostly on talking about starting with gallium nitride and going to diamond as far as wide bandgap materials, as far as work that we've done in the past. This is just a snapshot of the center. It's a multi-university center, including in the US and including Bristol University. And all these groups are working on different aspects of ultra-wide bandgap materials, primarily in material synthesis, heterojunction of these materials, the transport properties of these materials in terms of electrical transport, in terms of a thrust on high field transport and breakdown, and also a thrust on thermal transport and the thermal transport properties. So let me talk about device simulation, because this is what our group is primarily involved with. And device simulation involves basically the simultaneous solution of transport equations with electromagnetic fields. That is that you have a device domain, and you have a certain potential and field across that domain, and that leads to transport, non-equilibrium transport of electrons and holes. And that transport is described at different levels of hierarchy, which I'll talk about next, but there's various methods for solving transport equations, going from drift diffusion to non-equilibrium Green's functions. And transport equations themselves have to be fed by the underlying properties of the material of interest, and so that means the electronic structure in terms of the band structure, but also the lattice dynamics in terms of the electron-phonon interactions and the dispersion relationship of the phonons that are important for transport. So solved simultaneously in a self-consistent fashion, then the solution of transport equations with the electromagnetic fields, which can be either quasi-static Poisson solutions or more sophisticated high-frequency applications, finite difference time domain or FEM methods for solving Maxwell's equations. The simultaneous solution of this is then what is involved in device simulation, which leads to then a description of externally measured quantities associated with devices, such as the current voltage characteristics, transconductance, and different metrics of the frequency, like the cutoff frequency. So this is the basic approach, and again, it's a simultaneous solution of all these. In terms of transport, there's various levels going from exact and very difficult to solve to approximate but easy and fast. And so this starts at the very bottom by the direct solution of the Schrödinger equation, which is extremely limited, but then at the next level is the non-equilibrium Green's function method, which is becoming increasingly popular now. Louisville solutions of the quantum kinetic equations, the Wigner function approach is one that's very commonly used now by many groups. And then there's approximations of classical description, quantum hydrodynamics, etc. And then as you go up, there's semi-classical methods, which is the Boltzmann transport equation is the sort of master equation governing semi-classical transport, meaning that we can describe particles primarily as discrete points that we can follow the trajectories of, and then moments of the Boltzmann transport equation lead to the hydrodynamic and drift diffusion equations, which are used in commercial TCAD simulation. And of course, compact models then can be derived from drift diffusion, hydrodynamic, etc. in typical commercial packages to do circuit simulation based on compact models that are based on these properties. So this is sort of the hierarchy. And what I'm going to talk about today is that we are working primarily at the BTE level. That is, we use what's called Ensemble Monte Carlo or Cellular Monte Carlo in our case. And this is a mixture of quantum mechanical and semi-classical because we use a quantum mechanical description for the electronic structure and the solution of the phonons, etc., scattering rates and so forth, but we still treat particles as discrete quantities. So in the Monte Carlo, for those of you who are not familiar with it, in the Monte Carlo method, basically it's a stochastic solution of the Boltzmann transport equation in which the transport or the histories of individual carriers are treated as being decomposed into free flights in which they travel ballistically under the influence of whatever the local electric and even magnetic fields are, according to the Lorentz equation. What's accelerated is the wave vector, not the velocity itself, because of course, in a full band description, these are separate quantities. And then these free flights are subject to what are assumed to be instantaneous and memorily less scattering events. So this is Markovian approximation. And so these scattering events are generated stochastically using the random number generator on the computer according to the quantum mechanical probability of scattering. So there's many different types of scattering mechanisms in semiconductors that we have to be concerned with, but primarily we have defect scattering on one side, which is due to ionized impurities, dislocations, alloy scattering, etc. And we have lattice scattering, and lattice scattering has primarily optical and acoustic. They can be decomposed into intervalley and intravalley, but this is more of a multi-band effective mass type of description, and really what we're primarily concerned with is acoustic and optical phonons, and these can be either polar or non-polar, and can be, in the case of optical and for acoustic, this can be a non-polar deformation potential type, or there can be piezoelectric. So these are all important mechanisms that have to be considered. So lattice scattering is ultimately the limiting mechanism for transport, because it's a fundamental property of the crystal as opposed to defect scattering, which depends on the crystal quality. So in early stage technologies of materials, it's often the case that defect scattering dominates the transport properties such as mobility, etc. But ultimately, as material quality gets better, transport becomes limited by the phonons, by electron phonon scattering, and therefore, to understand the ultimate limits of possible performance, we need a good understanding of transport limited by electron phonon interactions. In terms of the Monte Carlo method, we use what's called an ensemble method, in which you simulate many thousands of electrons simultaneously, and you follow their history in a time-stepping fashion. So it's a time domain method of solution. And you start with some initial distribution of particles at a time t equal to 0, and then subject to whatever the electric fields are locally, because you can simulate the particles both in real space and in their trajectories in momentum space or K space. In other words, it's a six-dimensional space that particles travel in. At each time step, or during each time step, so there's when we say synchronous ensemble Monte Carlo, we introduce a fixed time step. And over each time step, there can be scattering events and there can be free flights. And so the little squares on this picture indicate scattering events, and the solid lines indicate free flights. And so you follow the trajectory of each particle or each time step, and you do that for all n particles. And then at the next time step, you synchronize them in terms of quantities that depend on the total distribution function of the particles, like screening. And then you proceed to the next time step. And so doing, you as you march forward in time, you can, for example, device simulation, eventually reach a steady state and calculate steady state properties as ensemble averages and time averages when you're in steady state, if you have an ergodic system, such as the velocity, and the velocity is related to the current, so you can calculate the current. You can calculate the current leaving the particles leaving the device and entering the device in terms of the terminal characteristics, etc. You can monitor what the velocity is as a function of time. So since this is time domain simulation, you can also have the transient information, which is important for doing high frequency modeling of devices. So that's a big advantage, is the time domain allows you to do frequency dependence, but also is a limitation in terms of you cannot do processes that involve very long times. And so Monte Carlo simulation is good at treating scattering events and those things that occur on a picosecond time scale. But when transport is dominated by, let's say, recombination that occurs at nanoseconds or microseconds or even milliseconds, then it's very difficult to use Monte Carlo in a direct fashion. You have to use some statistical averaging tricks. Anyway, that's the basis of Monte Carlo simulation. And then I want to turn to what we use, which is full band Monte Carlo simulation. And this was first popularized by a book by edited by Carl Hess back in 1991. And there was a lot of work in the late 80s and early 90s on taking what had been an effective mass approach to Monte Carlo simulation in the 70s and 80s and making it full band. The idea is that you use the full dispersion relationship for when you accelerate particles according to the block acceleration theorem, which I described earlier. And in doing so, you have an accurate description of the velocity as a function of time in terms of the actual band structure shown here. This is the band structure, for example, for gallium nitride. And what one has to do is, and the scattering rates are calculated between block states rather than as free electrons. And in the early stages, semi-empirical methods were used for band structure, such as tight binding and empirical pseudopotential methods. But increasingly, as I'll talk about, ab initio methods are now being used for the electronic structure. In any case, the process for full band simulation has a computational bottleneck, and that is that once you choose a type of scattering, you have to first choose the type of scattering using a random number among all the different probabilities at a given energy, but then you have to search the final state, which conserves energy and momentum across the entire Brillouin zone. And that's non-trivial because it's not a regular structure and has multi-values and band crossings and etc. And so searching the entire Brillouin zone to find the final state in real time algorithmically slows down this approach. So what we did back in 2000 was develop with Marco Saroniti, primarily did this as a postdoc at that time. That was to develop a what's called Cellular Monte Carlo, and the main difference is that what we do was to use RAM, which has become increasingly less expensive, and to basically store every initial for scattering events, choose every initial K and every final K prime across the whole Brillouin zone. And so basically you're storing n squared, where n is the number of points in the Brillouin zone that you're using in your electronic structure calculation. You have basically n squared of these, which is quite large and can be hundreds of gigabytes. Tricks have been used using integer representations and throwing away scattering events that are very small, you can save a lot of time, and so it's practically doable, especially on computers nowadays, which have large memory, large active memory available. So it's computationally fastest comparison of the CMC to ensemble Monte Carlo, and you can see it can be up to 100 times faster at very high fields when there's a lot of scattering occurring. Finally, in terms of device simulation, what one has to do is to solve the transport portion simultaneously with a field equation, and this is just an example using a Poisson's equation in which the device domain is represented by a mesh, just like in typical TCAD simulation. But in the Monte Carlo simulation, you have to track the trajectories across this, and so there are some tricks in terms of mapping the charge onto the discrete charge of the particles that you're simulating onto the finite mesh, and doing so in such a way that you don't have self forces that lead to errors algorithmically. And there are different ways of solving Poisson's equation that are efficient, like multi-grid and conjugate gradient, which can be quite fast. So we use this as well to do 2D and 3D device simulation where necessary. So let me start talking about some early work we did in the 2000s on gallium nitride, and then I'll talk about diamond later and try to keep on time. So, of course, gallium nitride has many applications in terms of high voltage, high frequency, applications in LEDs and lasers for optoelectronics, and also can be operated at high temperature. These are all properties that make wide bandgap materials useful and important for a certain class of electronics today. So what we did is to look at transporting gallium nitride using full band simulation using the Cellular Monte Carlo method, in which at the time we used empirical pseudopotential method in terms of calculating the band structure. And so the empirical pseudopotential method basically uses or has approximations on the pseudopotential in which the coefficients of the pseudopotential are fit in order to get the proper band gaps and other important transition energy. So it's empirical in the sense that there are fit parameters in terms of the actual pseudopotentials themselves that are used to get a band structure that agrees with the experiment. And so that's what's been done over years using the empirical pseudopotential method, and the same for the tight binding method. The phonon dispersions are also similarly semi-empirical, where there's different valence force models and Keating potentials, etc. And the one that we use here is called the valence force model, and this is the results for gallium nitride, which is more complicated than typical crystals, cubic semiconductors, because it's a word-side structure, and so it's less symmetric, and so you have 4 atoms per unit cell, which leads to a number of different or more, let's say, phonon modes than you would have for a material like silicon. So a method that was used earlier by Max Fischetti and the group at Illinois is a method called the rigid pseudo-ion method for calculating what the electron-phonon interaction is. And the idea of the rigid pseudo-ion method is that you can calculate what the deformation potential is by taking the electronic structure and shifting it with respect to itself. In other words, straining it, and in doing so, find the change of the energy band energies, and you can do this as a full function of wave vector across the entire B1 zone. So you can calculate the full anisotropic rate using the rigid ion method, and this is just the mathematics showing how you calculate the matrix element. And the deformation potential is now, instead of a constant, the deformation potential is a quantity that describes basically the change of energy or the scattering potential as a function of a deformation of the crystal, either by the optical deformation, which is the one sublattice against the other, or acoustic modes, which are long, in phase motion of the basis atoms. In this case, this delta is the deformation potential. It's a function of k and q of the initial and final wave vector after scattering. And so this can be shown to be this deformation potential can be determined by basically the coefficients, these C's, CKs, etc., are basically, and VK are basically the pseudopotential and the coefficients of the wave function at each k vector. And so this uses both the eigenvectors of the phonons and the wave vectors of the electrons to calculate this. So it's computationally intensive, but it gives a first principle of, quote, first principles. It's still a semi-empirical method, first principles way of calculating the electron phonon scattering rate. Then typically other scattering mechanisms that one has to worry about in gallium nitride are polar optical scattering, because it's a polar material, which is actually quite strong. Dislocation scattering, because there is a large epitaxially grown gallium nitride has a relatively high density of dislocations, and these can scatter and lead to a reduction in mobility. Piezoelectric scattering, again, because it's a polar material, and impurity scattering. So we use this in the cellular Monte Carlo method to calculate the velocity versus time, and then use that to calculate the steady state quantities, the velocity versus field. And so what's shown here is the calculated drift velocity as a function of electric field. Experimentally, that was measured here at ASU in our group using pulse IV measurements on etched gallium nitride samples. This was work done by Joy Barker for her dissertation. And the blue is the phonon limited mobility. And so you can see there's quite a difference between the phonon limited mobility and the actual experiment. And so what one has to do is then consider impurity scattering based on best estimates of what the impurity density is, including piezoelectric scattering also helps. And then, because this was just the polar optical and deformation potential limited drift velocity in the blue. And finally, with piezo and dislocations, based on the measured dislocation density of those materials, you get fairly good agreement with the velocity field characteristic. And so this was some of the first velocity field data that was available for gallium nitride. And this just shows the process of fitting the velocity field characteristic by including different mechanisms to find out what is limiting the mobility at low fields and saturated or the peak velocity at high field. So we use this simulation method then to do device simulation. So this was some work that we did in collaboration with Palacios's group at MIT. This is a device that they had reported IV characteristics for and high frequency measurements on. It's sort of a simplified schematic of the device, but it's a gallium nitride with aluminum gallium nitride barrier, hemped device with this particular one had an indium gallium nitride back barrier to help with confinement. In any case, so using the algorithm that I talked about, where you self-consistently solve the transport simulation by Monte Carlo with the Poisson's equation, you can see that you get a good agreement between experiment and simulation. The actual agreement wasn't that good until we included also a Fourier thermal model into the simulation. And because one of the things about power devices is that they generate a lot of heat, and because of the generation of a lot of heat, you get a phenomenon called self-heating, which causes a collapse of the drain current voltage characteristics, particularly in saturations. Not so much a collapse as a reduction of the current because of self-heating, because the local temperature increases. And this is something also that Dragica has done a lot of work on over the years in terms of doing thermal models and coupled with Monte Carlo to understand this effect. In any case, what's we shown here are simulations of the frequency characteristics, and the way that one does frequency simulation is, since this is a time domain simulation, one can introduce a pulse, for example, between the source gate and looking at the response of the source drain, and do this, for example, in the same configuration that you do for calculation of FT, the cutoff frequency, which is basically under short circuit conditions. And so you can bias the source and drain appropriately for short circuit conditions and calculate then the current gain as a function of frequency. This is the experimental result, and this is the simulated result. And you can see that you get excellent agreement in terms of the frequency response of this gallium nitride, aluminum gallium nitride HEMT. Okay, so I'm going to turn now to the last part of this talk and talk about diamond. And diamond is maybe the main ultra-wide bandgap material that we work on here at Arizona State University. We have a large effort headed by Bob Nemenich, who's also the director of our EFRC. And Bob has been working on a diamond for a number of years and has a number of growth systems for growing diamond that we use then for making devices and characterizing them. The main advantages of diamond are that it has, of course, a high breakdown field shown here. So what's shown here is this is sort of a spider plot of comparing different materials with different axes corresponding to different figures of merit: hole mobility, electron mobility, breakdown field, coefficient of thermal expansion, thermal conductivity. And what's shown in green is GaN. What's shown in the gold is 4H silicon carbide. Silicon is shown in gray, and diamond is shown in red. So diamond has several advantages. One, of course, because of the large band gap, the breakdown field is much higher. It's predicted to be as high as 10 megavolts per centimeter, just based on the band gap. And that's one of the things that we're trying to determine theoretically by using first principle cellular Monte Carlo. It also has a electron mobility and hole mobility that are quite high compared to other bulk materials. That both the electron mobility and hole mobility are close to 2,000, and some experiments even say higher than that. And that basically having both the hole mobility and the electron mobility high is advantageous, of course, for complementary devices, but overall leads in terms of power electronics to superior R-on, meaning the R-on, which primarily depends on mobility, is going to be less, and that means that the figure of merit will be higher. Another big advantage of diamond is that its thermal conductivity is the highest of any semiconductor. And that's actually something that we are working on as part of the work under the EFRC. Besides looking at electrical transport, we're also looking at thermal transport, also from a particle-based approach using cellular Monte Carlo, and trying to understand from first principles what limits the thermal conductivity and what things, how do impurities, isotopes, etc., affect the thermal conductivity, as well as defects. All these things together mean that if you do a comparison of on resistance versus breakdown voltage on a log-log plot, this is one way that people used to use this figure of merit that I mentioned, VB squared over R-on, as a relative comparison of the quality or the relevance of a material for power electronic applications. And so on this axis going to the right means you have higher breakdown voltage. On this axis going down means that you have lower R-on resistance. So the most desired place that you want to be is in the lower right-hand corner in terms of your on resistance and your breakdown voltage. Here's different materials: silicon, gallium arsenide, gallium nitride, beta gallium oxide, etc. And diamond, of all those materials, and maybe aluminum nitride to some extent, ideally have the best figures of merit in terms of being the farthest over on this curve, meaning that they have both high breakdown voltage and low on resistance. And so that makes them materials, that makes this material particularly interesting for power electronic applications. This is just some work, experimental work that we've done at Arizona State University in collaboration with Srabhanti Chowdhury, who was at ASU but is now at Stanford University, and these are basically breakdown characteristics of different PIN diodes that have been fabricated on diamond. One of the unique capabilities at Arizona State University that Bob Nemenich's group developed is phosphorus doping of diamond. Previously, only P-type boron doped diamond has been available and has good transport properties, but recently now there's been a lot of work on phosphorus doping and being able to achieve fully bipolar devices. And so these are what we call fully depleted PIN diodes. So the N region at the surface is depleted. So it's sort of a combination of Schottky and PIN diode. But anyway, we've measured breakdown voltages in excess of 1,000 volts, which means that you have breakdown fields greater than 3 megavolts per centimeter, which is still less than what theoretically you should have, because theoretically, at least just on simple considerations of the band gap, the breakdown field should be on the order of 10 megavolts per centimeter. Of course, breakdown field is not a single constant. It depends on doping and device configuration and things like that, but in that range. And so, some of the problems are the fact that material quality is not mature compared to, say, silicon and gallium arsenide. And so breakdown doesn't necessarily occur due to avalanche breakdown, which would be the limiting mechanism. Avalanche occurs due to leakage currents and things associated with transport along defects. And so the idea is to improve the material quality and try to reach the limits set by the band gap and avalanche breakdown as the ultimate mechanisms, and that's what we're involved with theoretically trying to predict. I should also mention that our group has also demonstrated the highest current density of any diodes. That is what's shown here are the current density versus voltage of the Schottky PIN diode with a very thin I region, which achieved close to 1,000 kiloamps per centimeter squared, which is a record in terms of forward current density. So again, this is just part of the reason that R-on is relatively low in these materials. They can handle a high current density without breaking down, also because of the thermal conductivity, which keeps them from thermally breaking down. So what we've been doing is to try to go beyond empirical methods I talked about, using tight binding or empirical pseudopotential, and do Monte Carlo method, do Monte Carlo simulation directly from density functional theory. And so the idea is that we use density functional theory and extensions of that using using the GW method in order to calculate more accurately the electronic structure and as well as the electronic structure of the phonon dispersion, which you can also obtain from DFT. So density functional theory comes from first theories. It makes the many body problem a one electron problem by introducing basically a functional method that is writing the total energy in terms of a functional of the electron density, and then minimizing that in order to calculate the ground state. So density functional theory is, first of all, an equilibrium method. So one has to question when we're using this for high field transport whether the band structure actually stays the same, or whether one has to go to some even beyond ground state theories. And there's time dependent perturbation theory, and there's people working on this problem. We are just working right now with the basic density functional theory, and so this is a ground state method. And as such, it's good for the ground state properties, but The conduction bands of typical semiconductors are excited state properties, and therefore they're not as well described by DFT. And so DFT historically has suffered from the fact that the band gaps that are predicted from DFT are almost always less than the actual experimental band gaps. And so therefore the GW method is a perturbative approach, many body approach, which uses the DFT results as basically the starting point to do a perturbative expansion on and calculate the contributions of the excited states. And so this is shown of its accuracy to be quite accurate in terms of predicting the band gaps of semiconductors across a broad range, from narrow band gap to very wide band gap insulators. And so we use then DFT combined with what's called the Berkeley GW, which is one particular package that does GW calculations to calculate the electronic structure. Interesting thing is this is a comparison of the red is the DFT calculation. The blue is the GW, Berkeley GW. I forgot what the black is. Maybe it's experiment. But in any case, the red curve, the DFT has been shifted, so-called scissor operator. It's been shifted to give the same band gap as the GW calculation, which is close to the band gap of diamond, what we get from GW calculations. What you see is that the actual details of the band structure are not vastly different between DFT and GW. The main difference appears to be the details of basically the band gap itself, which is just kind of an interesting observation we noticed. As far as the phonons within, for example, the package we use is Quantum Espresso, but there's also VASP and other DFT packages available. Within that, we use what's called density functional perturbation theory to calculate the phonon dispersion. And so what's shown here are various approximations of different starting superpotentials within the DFT method. And it was difficult to get a good agreement with using the exact band lattice constant for diamond, but there was a paper by Pavone et al. Which used a relaxed lattice constant, allowed the DFT to relax slightly to a lower energy value, and that actually gives a good agreement with the measured dispersion. The dark circles are the measured phonon dispersion from neutron, inelastic neutron scattering. So we did find that if you use something called ultra soft pseudopotentials, that you can exactly reproduce the experimental points without relaxing the lattice constant. However, unfortunately, the ultra soft pseudopotentials aren't compatible with the Berkeley GW, and so therefore we couldn't use that. So we used instead this relaxed approximation. A side project we did was associated with what's the effect of boron doping on the phonon dispersion. And the problem, or the issue is that, and this has to do with thermal properties, is that typically in terms of doping, that very high doping is used to get high conductivity diamond by doping at doping above 10 to the 19th, for example. And what happens as you get up to 10 to the 20th, one notes, or experimentally have noted, that the thermal conductivity degrades significantly. And we've been looking into that, and just as an aside, we included basically within this DFPT approach, we included boron doping by using a supercell method, which means that you put an atom in and then reproduce, put a boron substitutionally in and create a cell that you reproduce, and the size of the cell determines the effective concentration of the boron. But at very high boron concentrations, you see actually quite a significant softening of the phonon modes and a decrease of the optical phonon modes. So there's a significant effect onto the phonon with very high doping, which is something we're looking into as well. So the next thing I mentioned is that the breakdown voltage in an ideal material is limited by what's called impact ionization scattering, in which a high energy electron or hole has sufficient energy to excite an electron hole pair across the band gap. So there's two methods that are being used in the literature right now in terms of first principles methods. One is to use a screened Coulomb interaction, which is what we're doing presently. There's also a method based on taking directly the self energy from GW calculations and looking at the width of that and relating that to the impact ionization rate. We haven't been successful in using that method to date, so we've gone with the screened Coulomb interaction, which has also been used by Belotti's group for some simulation of breakdown or impact ionization in gallium nitride, for example. And it basically comes down to that the scattering rate for impact ionization is written as a screened Coulomb interaction. In other words, the particles interact with each other through see each other through a screened interaction, and that so down here, this matrix element, which includes exchange direct terms and exchange terms in terms of electron-electron scattering, conserves energy totally. That's the delta function here, and conserves momentum overall in terms of the initial and final Ks of the initial and two final particles. And this term here in the matrix element is basically the Coulomb potential, described by screening through a frequency and wave vector dependent dielectric function. So the first problem is, what is this function, and what do we use for that? And then computationally, the second part is that you have to integrate over three coordinates, and so it is computationally fairly taxing, but doable. As far as the screening, what we use is the full band Lintard dielectric function. So we use the full GW wave functions in order to calculate this. And in this approximation, the Lintard dielectric function as a function of Q and omega can be written as this summation over delta K band indices and yes, conduction and valence band indices. So there's a real part and an imaginary part, and this is what the calculated real and imaginary parts look like as a function of frequency for different wave vectors. So normally the usual approximation is using the long wavelength limit and omega going to 0, which is down here, and that would be the typical that would be the static dielectric function. As you can see, as you get to high energies, that you start to have significant contribution to the frequency dependent part of both the imaginary part and the real part. And normally that wouldn't be a problem for narrow gap material, but when we talk about diamond, where the band gap is already 5.5 eV, so that means that you have to have 5.5 eV above the conduction band for an electron to excite a hole from the valence band. So you have typical energies involved of 5 to 10 eV, which is actually out here. So it turns out to be very important that you include the full frequency dependent contribution of the dielectric function and not just make a static approximation. So this is the calculated impact ionization rate for electrons and holes from that process, and that's compared to some similar work that was done in Japan at Osaka University in Mori's group, and you can see that it agrees quite well. So we're pretty confident in terms of our impact ionization rates. And then the important thing then in terms of what limits or what determines the impact ionization coefficient is the phonon scattering. And so this is the expression for electron phonon scattering in terms of the deformation potential, which is shown here, overlap factor for the different block states. I'm sorry, this is the deformation potential, this is the density of states. So this delta is the deformation potential. So the first thing we did was just to consider constant deformation potentials. So this is two sets of deformation potentials that we found in the literature for the acoustic and the optical for electrons and holes. So there's 4 different parameters. So the orange are one set and the blue are another set. So you can see that you get 2 different quite different scattering rates for these two different sets of deformation potentials. So we use these deformation potentials together with this calculated and fully anisotropic impact ionization rate to simulate the impact ionization coefficient. So the impact ionization coefficient is basically a measure of the number of electron hole pairs per unit length that an electron or hole is traveling in the crystal. So it's like a generation rate due to the movement of carriers through the crystal. And so that's the definition of the impact ionization coefficient, and it's defined in term as a function of electric field, and changes exponentially with that. In fact, typically what's used in TCAD simulation is some form of Chenoweth's law, which has an exponential relationship of the impact ionization coefficient on the electric field. In any case, we use these two different sets of rates into the Cellular Monte Carlo code and got vastly different impact ionization coefficients, orders of magnitude different, as you can see, which led us to the conclusion that besides the impact ionization rate itself, which is the one that depends most directly on the band gap, that the electron phonon scattering rate plays a critical role as well in terms of determining what the impact ionization coefficient would be. And you know, this range of impact ionization coefficients goes from like 3 megavolts per centimeter to 10 megavolts per centimeter, so it's quite a range, even though it's for the same band gap material. So again, this just points to, which we didn't appreciate before, that the electron phonon strength plays a critical role in terms of the impact ionization coefficient, because obviously the more phonon scattering you have, the cooler the distribution remains and the lower the energy of the carriers are that can contribute to band-to-band excitation. So this is the last slide. Basically, where we are right now is that now we have used what a recent method that's been developed by Giustino's group at UT Austin is called the EPW method, which stands for electron phonon using Wannier functions. This uses directly the output, or uses directly basically the DFT solutions from Quantum Espresso, and we've extended that now to include the Berkeley GW method in this as well. In any case, the EPW method calculates the electron phonon scattering rate directly from basically it's a matrix element of the derivative of the self-consistent potential with position. And so this deformation potential is calculated between every k and k prime. So it's similar to the rigid ion model in that it's a fully anisotropic electron phonon scattering rate. And what we do is extract the deformation potential from that to use right now currently in the CMC code, which unfortunately I don't have results I can give right now, but what I can show is that this red curve is the actual electron phonon scattering rate averaged over all k for a given energy. In other words, averaged over constant energy shells. This is this red curve is the direct electron phonon scattering rate from EPW, and the orange and the blue are the two sets of deformation potentials that I showed you. So interestingly, it lies between the two deformation potentials for electrons and is slightly higher for the holes. So the expectation is that the set of impact ionization coefficients, once we get this imported properly into the CMC code, will be basically somewhere between these two sets of curves, which ideally would be what we expect. It would give more of a reasonable critical field for diamond, which would probably be in the let's say 8 megavolt per centimeter range, which would be appropriate for that material. So that's basically where I'm going to end, and just say that you know, we've been using this method for 20 years now to look at transport and wide bandgap semiconductors and materials and devices. What's the main trend has been over the last few years is moving from semi-empirical descriptions to more first principles approaches, as the capability of first principle calculations has rapidly evolved over the past decade. And so we're trying to take advantage of this and utilize this directly in the transport description. The recent work has been focused on trying to extract electron phonon interactions from first principles and use that directly instead of making or using approximate deformation potentials. And so, one of the things that I noted just in the previous few graphs was that for wide bandgap materials, the exact strength of the electron phonon interaction is actually a crucial quantity in simulating the impact ionization coefficient, and hence determining the figure of merit for these materials. So with that, I'll stop and I'll be happy to answer any questions that you might have.
Thank you very much, Steve. This was fascinating, and it's amazing how much progress has been made in this field, and the contributions that that your team has made. So we have time for questions. So please type your questions in the Q&A or chat box, and we can ask Steve. Steve, I have one broad question. So it's fascinating that now you can make so many calculations and get good agreement with experiments on some very complicated phenomena. Could you say a few words about now, with this much understanding, what kind of predictive work or predictive results this kind of modeling can provide us to guide material and technology development?
So one thing that we're doing that's part of the center, once we get this, where we believe the results recently for diamond, there's more materials that are much less well characterized, and we have much less knowledge about, that we would like to make predictions about their figure of merit quantities, such as low field mobility and breakdown voltage. And so we're moving to boron nitride very shortly after this, which is even wider bandgap material that almost nothing is known about as far as these properties. Looking at aluminum nitride, which also is relatively unknown as far as these transport properties. And then there's a variety of oxide materials, and gallium oxide in its beta form is just the first, but there's alpha gallium, alpha phase gallium oxide. There's other oxide materials which may serve as wide bandgap materials as well. So I think that's where we're moving next, is to move to unknown materials and try to predict whether they're worth pursuing as far as power electronics, for example, or for other applications like high frequency applications.
Great. And for example, are you thinking about, with the same material, changing the conditions, like applying strain, or change the growth mechanism, or altering some conditions that might result in better performance?
Yes. So one of the things that we're concerned about is that a material like diamond has a relatively high level of, let's say, point-like defects associated with nitrogen incorporation, oxygen incorporation, things like that. So it's entirely possible that these types of defect in the material may contribute to a lower breakdown than you would have just from band-to-band impact ionization. In other words, they provide an intermediate level where you could have impact ionization that occurs at lower fields than what's necessary to excite an electron across 5 eV. So it could be a two-step process. So we're looking at trying to calculate what the defect-assisted impact ionization rate would be, for one thing. As far as just the transport properties itself, we want to understand the role of these defects in limiting the mobility, limiting the velocity field characteristics, and ultimately, what in device simulation, how it affects the device performance.
Great.
We do sometimes go back and forth between using, for example, the CMC method for getting fundamental quantities like mobility, and and saturated velocity and things like that, and then using that in say Silvaco or Centaurus to try to do more complicated device simulation, just as for the sake of expediency. So sort of a hierarchical approach as well.
Great, thank you. So we have one question from the audience, and it's an interesting one. So what's your opinion on the potential of quantum computing for semiconductor simulation, DFT, or nanoscale modeling?
That's a good question.
Specific
I'm not sure myself, although I know that quantum computing has been applied to simulating quantum systems by mimicking their sort of behavior. So I know it's been used in quantum chemistry recently to try to simulate the evolution of a system of atoms by sort of mimicking that with qubits. But so I think that's maybe so transport simulation may be a place where quantum computing actually may have an application. There's relatively few algorithms otherwise in terms of quantum computing, but this simulation of quantum systems is kind of intriguing. And we're keeping an eye on it, but it's still pretty new.
Yeah. I have more questions, but I want to see if Daragitsa has any question that would like to ask.
Yes, I am actually interested because you mentioned that it requires CFC method a lot of memory, and I that was constrained in the past. How much of a constraint is nowadays because RAM has become significantly cheaper?
Yeah, that was sort of a guess that we made back in 2000 that in the future that memory was going to be a lot cheaper, whereas CPUs wouldn't advance that fast, and that turned out to be a correct assumption. And so a lot of algorithmic stuff that was built in the code to save memory back in 2000, when we were limited to like 10 gigabytes per processor, now we have 200 gigabytes per processor. It's much less of a constraint, and you can do bigger systems, use a better discretization of the Brillouin zone, for example. So it's helped a lot, really, that memory has become so inexpensive, relatively speaking.
Yes. Maybe another follow-up question. What actually is incorporated in terms of self-heating in the CMC code?
So right now, we're not using it. Well, there is some work being done. There's some variation of the hydrodynamic approach that you used. That was used by one of the students recently, and that was used for looking at like self-heating in HEMPs, I think.
Okay.
So it's kind of this hydrodynamic approach that you developed. A little different, but similar. Then there's been some students that worked on full particle-based phonon transport. That was coupled to the electrical part, but that's really hasn't been tested as far as self-heating, because it's a very difficult problem. The thermal part works pretty well. The phonon Monte Carlo, that works fairly well. The electron phonon, I could say that the main difficulty is the fact that the weight of phonons compared to the weight of electrons in a typical device domain is orders of magnitude different. And so that leads to some problems of electron phonon coupling when you have particles and particles.
Exactly, yeah. Any other questions from the audience? I see a couple of people here.
I guess we are a little bit over time,
Okay.
and maybe that's a sign that we can wrap the session up. Thank you very much, Steve, for the fascinating presentation and a lot of insightful ideas.
Well, thank you
Really
for inviting
appreciate
me. It was a pleasure.
Thank you.
Okay.
Thank you also, and thank you to all of our attendees, and check out the NNCI events page for future webinars. Thanks, everybody.
Okay. Bye-bye.
Bye.
Thank you. Bye.